Hello and welcome. My name is Volker Muehlhaus and I want to show you Empire XPU, the very fast EM solver used for RFIC applications. This is a chip sitting inside a recessed hole on a PCB, and we will look at some basic Empire features used to simulate this example and to edit it. Okay, so we do see a 3D view here. We see different metal layers on chip. We see bond mice, we see PCB stuff. And we have a 3D view, but for some of these 2D features, the 2D editor is much more convenient. So where is the 2D editor? We can go to 2D design. So here now we have different 2D views. We have the top view, we have a side view of the setup. So this might be more convenient for 2D layouts like on-chip layout to use this 2D editor instead of 3D editing. Our chip is a layered structure. We have many different layers in our RFIC editor, so it does make sense to have these layers also in Empire in our editor. So here we go to groups, and if you use my template for the IHP technologies, you will have this structure here. So we have the metal layers, metal 1 to metal 5, top metal 1, top metal 2. We have the via layers. And in this example, we also have some PCB layers for the PCB part. What is a layer here? It is a definition of material. It is a definition of the vertical position in the stack up. So this brings together the 2D layout with the rest that is required for simulation. To draw on a layer, we just select that layer. So for example, here we are on the PCB top layer. So we snap to this point, we draw this rectangle here, and we go to create box. If we want to do a cylinder, we can draw this radius, create cylinder, and here we go. If you want to edit after the fact, select it, open object. The radius is, for example, 100, and it's 100. If we want to move an object to a different layer, select the object, go to this here, copy move, keep object on original group, no, set to group height if possible, yes, and now it's on the via layer instead of the PCB top layer. So very, very simple. So we move it. Let's look at some more features of the 2D editor. So we had seen that we can create an object just by dragging the arrow with the size that we want. So for example here, horizontal size 300 micron by 255 vertical. Go to the layer where we want to create this object. So PCB top, create, and here we go. If we want to resize it, we can click on that edge. We see the green handle. Now we can easily resize this. Stretch by -200 to go left, and it's stretched. Very easy. There's also parameters, which is discussed in a separate video. To use the 3D editor, we have a little bit different logic. So in the 3D editor, by default, we always snap on the topmost object that is under the cursor. So here in the bottom left, you see the Z positions, the vertical position. If I'm here, I'm on the substrate. On the PCB substrate, it's 245 micron height, and here I'm at 271. So here my cursor snaps to the top surface of the PCB top layer. So if we want to create a bond wire, for example, I go to the group bond wire to have the aluminum material, then create library object, bond wire, from here to here I have my bond wire, and another one from here to here, for example. So these are my bond wires created by snapping onto the topmost object underneath my cursor. Okay, I delete this because this obviously does not make much sense to short my signal line to the ground conductor. But you have seen, so we can draw the 2D objects easily in the 2D editor by using the layers, or as it is called in Empire, by using the groups here. And the 3D objects are very easily created in the 3D editor. Of course, we can also create 3D objects in the 2D editor and 2D objects in the 3D editor. You can switch to the editor that makes most sense for your actual application. There are many 3D library objects. We had seen the wires, but we also have all sorts of 3D solids. We have 3D surfaces. We have extruded 2D objects. We have some typical microstrip elements. So if we want to place, for example, one of these objects here on the PCB top layer, by selecting the object, we get the parameters. So these are fully parameterized 3D objects. And let's look at a different example now to see one example with a dipole on chip using a dielectric lens. Here is the example using the dielectric lens. So what do we have? We have an SG13 chip sitting inside a metal box. So we created a little cavity here, and we have this lens on top. How is this lens created? It is created from a sphere. You might wonder why we use a sphere. That's a predefined element here. We can give it a diameter, and we can give it cutting planes on the top and bottom side. And by cutting this sphere in half, we have a lens. And by using parameters in a smart way, we can change the radius of the lens, and the lens scales as required. So the basic 3D library objects in Empire can be used to create a wide range of objects, which in this case are also parameterized. So what do we have here? We have the insertion point of this parameterized sphere, which is defined by using a variable, and the parameters itself, the radius or the diameter, it's also using a parameter. And here, this parameter in Empire, we can use to just sweep something by hand. We can use it for a actual parameter sweep. We can use it with the optimizer. So different options to use this parameter. Let's have one more quick look at parameters. so by stretching this dipole. So we drag a window as before. So select overlapping, stretch, and instead of using a fixed value, I now do minus dl for delta length. What is dl? dl is my delta length. It's minus 200 to 200 micron with steps of 50, for example. And then I do the same thing to the right side of the dipole. So stretch, and in this case I do dl, and here is my variable. So now I can modify this dipole. I could do the same thing on the other side. Let's do that. I select this, I drag a line of symmetry, and I copy and mirror. So now my delta L stretches both dipoles. That's it for editing for the moment. Overall, Empire is a 3D simulator. So let's look a bit at simulation. How to start a simulation. We know how to set up a simulation first. We go to simulation setup here. So we had defined a drawing unit. We had defined an EM solver, not thermal, but EM solver. The structure is an antenna, which tells Empire to use absorbing boundaries and some other settings that are antenna specific. The frequency range we are interested in 200 to 300 gigahertz, a target frequency of 245. What is the target frequency used for? For example, if we do a far field analysis, if we calculate the antenna pattern, the antenna gain, the field sampling will be preset to this target frequency. So then if we enter our frequency of interest here, we don't need to enter frequency again in the far field and antenna pattern dialogues. The losses, we simulate wideband losses for dielectrics and conductors, and we have absorbing boundary conditions, so that except for the bottom size of the substrate where we have a metal boundary, that all the other 5 boundaries use absorbing material, so that the energy radiated can be absorbed and sampled for pattern creation. When we are done, we can start the simulation using the simulation control, which I will not do here. And when simulation is finished, we get the result as a voltage in the time domain. Empire is an FDTD solver, so the primary excitation is a time domain pulse. Now I go to simulation again. So the pulse that Empire used is this Gaussian pulse, which gives this wideband spectrum. And when Empire has finished, the excitation and the energy in the system has decayed to a certain level, then it's doing a Fourier transform of this time domain signal and gets the S parameters we're interested in. So here are the S parameters from 200 to 300 gigahertz as requested. And once again, the primary simulation is a time domain simulation, and so we have a wideband result by doing the Fourier transform. So there is no price to pay if we want to have this more wideband or not so wideband. This has very little influence on the simulation time. More results here. We have a far field. So here, for example, is the gain in dBi in a rectangular in a rectangular representation, if we go for the polar plot magnitude in dB, we can select 240 gigahertz again, show only and auto color, and here we have the antenna gain in polar view. So we have the phi 0 degree and the phi 90 degree cut, and we can put markers here, and we have the gain of 11.5 dB at this 0 dB angle. So what else is of interest here? We can look at the antenna efficiency. So if we go to additional plots, scroll down, antenna efficiency, for every frequency point where a antenna calculation has been done, Empire also calculates the antenna efficiency and the radiation efficiency, that is the radiated power versus the power accepted by the antenna. Another parameter of interest could be the antenna gain versus frequency. Let me find that. It's not here. It is frequency domain far field. So here's the antenna gain in dBi as a function of frequency from 230 to 260 gigahertz. We also have a 3D view. We could do the antenna pattern in 3D view. We can do electric or magnetic fields or current densities in 2D view. In 3D view. We can animate this. And that's it for the moment. Thank you very much, and if you're interested, there will be some more detailed videos on different detailed topics. Thank you very much again, and bye-bye.